Thank you. Well, that's probably the only applause I get tonight. Wait until done with the talk. So, defending the poor is, and I'm saying that right away because I've heard a couple of complaints by other people saying that security talks are always like drama. They're building up and then you actually have to sit through them to actually get the exploit. So since this is a defense talk, we can break with this tradition. And so the purpose of this presentation is actually to discuss how to counter attacks based on rich internet applications in the example of the Adobe Flash runtime. And well, in short, this is not about Cisco. So, since I'm doing that the first time, I have to put in a disclaimer. Defense is new to me, as some of you probably know. And I'm not a Flash developer, which might not come in surprising. And I totally appreciate feedback about the work and everything, including feedback that says I should shut the fuck up and give the slots to other people. So, what are we talking about? We're talking about what's the motivation behind this research. So this is why I couldn't give it away before. It's part of the slides. Wouldn't fuck up my drama. We're talking a little bit about RIA basics and stuff, how Flash security works, what Flash malware types we're seeing. We're going to talk about the Flash internals. That's the fun part. Then we will talk about the defense approach. We came up with how we implemented it, what works, what doesn't work. This is actually code being developed, so of course it is not at the stage that I wanted it to be for today. And what we're going to do next. So what's the motivation behind this? So in late 2008, the German Federal Office for Information Security, or as we all know it, the BSI, actually initiated a project on researching the current state of security in rich internet applications. And given this audience, I would like to say one thing. We do all enjoy bashing the BSI and other government institutions, but you should not forget that Germany is one of the very few countries that actually has a government institution whose partial purpose is to make sure that the citizens and their computers are protected. All the other government institutions that we have in the world actually care about government systems and military systems and police systems. We actually have a quite capable group of people that cares about the general public. And we should occasionally consider helping them in their cause. So as I said, it was a review of RIA architectures and security, and Adobe Flash turned actually out to be a whole can of worms, and certainly behind the curve in terms of security compared to everyone else. Which of course posed the question, can we actually fix this, preferably without firing anyone at Adobe? So this is where it came from. Now the question obviously is, who cares about Flash security? One group of people is, well, the Apple users care about security at all? Let's assume they do. So one of them is actually Apple users still running PowerPC machines because PowerPC is not going to get any security patches anymore. The second group, which I belong to, is people who don't like to get owned just because they serve porn. Porn actually comes in a lot of Flash players, and we actually want it to, show the images, transport the audio, which is not very interesting, but part of the show. And still don't find new exe files on our Windows machine after we did so. The other group is less obvious. The other group is website operators, primarily people that actually get advertisement banners from other people, because those tend to be in Flash. And the problem, of course, is if you get fed parts of your website that you're including that are not yours, you might actually be in for a couple of surprises, as Heise, eWeek, and other large online sites should. Also, if you just own a website that allows people to upload stuff, you could potentially be held liable for the Swift files that people find on your website that do strange things to their computers. So, rich internet applications, what is it? So, essentially, in general, it's a programmatic way of enhancing your regular web browser with more interaction, media, display, linking. The prominent members here is the one with the F for fail, then Microsoft Silverlight and the Moonlight implementation, and Java, they violated a trademark there. So what's common about them? Commonly, the RIA functionality is implemented as a plugin. So the plugin provides an actual runtime for the specific RIA content. So you're thinking virtual machines. The RIA runtime additionally provides like media playback and other stuff. The applications in all three cases are, or the RIA files are actually distributed as a combined set of data for media, of code, of images, everything in one file. The runtimes actually run those files and then provide additional services that the browser actually intentionally didn't provide, which is independent local storage and independent network communication and all the things that your browser is not supposed to do. RIA applications are supposedly portable between operating systems as long as you have a runtime. So it is a plugin for most browsers. However, the runtime itself is relatively independent from the browser. So the runtime is usually implemented in an ActiveX or other type of DL. And then the browser only has a little bit of glue code, and the only dependence really being the JavaScript, the DOM, and everything else. The activation of that functionality obviously is by embedding some type of RIA content in your web page. And then the browser will know, hey, I have a plugin for this, so I'm going to fire it up and run. How are they distributed? The short sum of it is every fucking computer runs Flash, except for a couple that weren't detected. Silverlight and Java actually plays a bigger role. Silverlight actually doesn't play a big role so far. So what's the security model of Flash? Primarily, it relies on the idea that it has code that runs in a virtual machine, and then the virtual machine actually makes sure that nothing gets out into the native system. However, they also need to make decisions on what to do with data. So they have this concept of called sandboxes. So in principle, you can either live in the local or in the remote sandbox. If you live in a remote sandbox, you can talk to the network, but not to the file system. If you live in a local one, vice versa. The remote one roughly implements the same origin policy. It's commonly said it is the same origin policy, but if it were, I wouldn't stand up here. The Flash code itself, for example, for saying what can access my Flash cookies, the Flash code itself can say, dear runtime, I would like to soften my same origin policy. I would like to give access to the domain star to that cookie I'm writing, which obviously gives access to everything. The website that the Flash file actually came from can also soften all those limitations by placing a policy file within the same web server saying this Flash application can talk wherever it wants, as if the website is the one that should decide that. So you can actually pass additional parameters to it in the embed text saying, well, it's fine for scripting or it's not. To the user, this actually plays as very limited settings. So the user actually has very limited things to do. There is a setting dialog, which is an actual Flash application on Macromedia's website. What you actually have in terms of controls, and there are quite some, is hidden somewhere in the developer specification. You can actually find little pieces that say, oh, if you create this MMS, the CFG, obvious name, in a very specific location on your file system, then we will observe whatever is configured in there. Also, Flash doesn't have any proof of origin, like you can't sign Swift files. There is a likely exception with DRM, but we're not concerned about DRM here. So what types of vulnerabilities are we looking at when we look at Flash? Like, what do we actually have to fix? Well, you have a bunch of them if you go to, for example, Security Focus and lists like everything Flash player. And if you look at it, it says like, oh, you can arbitrarily copy data from the clipboard or to the clipboard of the user, or you have an integer overflow here, or you have the 2007 marked out bug, which is the integer signedness issue in their scene counter, which they have for 10 versions. It never would ever someone try to actually put a large integer in that field. So in 2007, Mark Dowd wrote this excellent paper and exploit on this. If you haven't checked it out, it's definitely worth a read. Nowadays, lately, those days, we have a couple of unspecified memory corruptions, which every unspecified memory corruption I ever heard of could be turned into an exploit. And in 2008, for example, we had a version null pointer dereference, and I was like, what the fuck is this? And I checked out the exploit, and you don't actually have to be able to code ActionScript to see that this is not a lot of code. And calling load twice shouldn't actually cause a null pointer dereference in a virtual machine. So what attacks are we seeing? Apart from obviously popping the player and straight executing code on your machine, Flash could be used in the past for DNS rate binding attacks. Dan made that happen. You actually see a shitload of Flash files that are used as exploit carriers. So since Flash has so many information about the versions of different parts of your operating system, like what operating system version down to the build number you're running, what browser down to the build number, what Flash version down to the build number, all that type of stuff, you actually see exploits that figure all this out and then grab the right exploit of a web server and execute it. You also see clickjacking, so the Flash actually overlays your UI, and then if you click on something, you actually clicked in a Flash file. We have seen a lot of cases with additional HTTP headers. So there was a very famous exploit that uses a CSRF vulnerability in a home router, like the little plastic boxes, that was largely shipped in, I think it was Mexico, Brazil or something. And so they had this banner ad that they placed on all the Brazilian files, and then everyone who surfed to the website actually owned his own router. The same works with UPnP. You can generate UPnP from Flash, and then whoever surfs to the website after that had a port forwarding through his NAT in the home router. The most common thing that we actually see is so trivial it hurts. It actually takes the browser and sends it to a new URL. So, and that also tells us what type of malware we are seeing. So the class 1 is actually the redirectors and downloaders. They just point the browser from whatever website the Flash was loaded from to a URL that ends in .exe. And as by the same theory of why spam is still around, if a large enough percentage of the people just clicks on open, they're good. So this is the most common thing you see. You also see binary exploits that target the runtime. That's usually based on Markdown's work, actually. Or you see the attack vehicle thing. So you have a cross-site scripting in a website, and the cross-site scripting by itself doesn't get you anywhere. But if you can make it look like your Swift file came from this website, then you can actually do a lot more shit. And so this is what people do. Examples, the most commonly seen malware, and that's also what hit Heise and eWeek and others, is something called Gnida. And it's a malicious banner ad that actually, it is actually not really malware. It's a piece of Flash code that checks with your local Flash cookies whether you have been part of the scam before or not, and uses different timings to execute clicks on other advertisement campaigns or download stuff to you. The other one is the 2007 0071 exploit, where we see countless variations of. And then you have the really easy downloader Trojans that just try to like hide what they're actually downloading, but don't do anything interesting. They're still annoying though. Now here's the interesting thing. Before we go into Flash details, let me tell you that like most of the Flash files internally are compressed with zlib. No voodoo, it is straight zlib. Now you take a couple of malware examples, I took 3, and load it up to virustotal.com, which runs through a shitload of virus scanners and tells you whether they detect anything. So you take a generic downloader, you fire it up, 18 out of 41 AVs actually detect this. The generic downloader has 2 instructions for the virtual machine. So it's not like the most complex piece of malware you've ever seen. Still, you got like 43% detection rate, or 44. You take the same file, you uncompress it, so it's still a valid Flash file, it's no longer packed, that's all, and it actually drops to 16. Now, you take the most common piece of malware in the whole Flash world and do the same exercise, 29 out of 41 detected, you decompress it, 8 out of 40 detect the most common piece of Flash malware. Turns out they're obviously really matching on the packed string, like the string that came out of zlib when it was compressed. So let's put it this way, the AV companies are not going to be much help in protecting against Flash exploits. So how do they look in the inside? Better. So, how does Flash look in the inside? The Flash file is also called movies, which is kind of like fitting, but I don't like it too much. Follow a specification called SWF, or apparently pronounced SWIF. Version 3 to 10 are specified, and I'm going to bore you with the whole history of this specification. They can be compressed, as I mentioned. They generally follow a TLV structure. Like everyone who has seen binary file formats knows that, or protocols. It's like type, length, value, and then you have a container object, which may contain other container objects. They call those things tags, well, at least the upper level. There are 63 of those tag types. And what's really important to know about Flash is everything is heavily version dependent. Like you take the same data structure, you take version 4 and version 5, the data structure looks different, the data types look different. So everything is massively version dependent. So what's actually executing code in Flash is what's called the Adobe virtual machines. And here's the first big surprise, at least it was for me. It actually contains 2 virtual machines. Like securing one would be so easy for Adobe. So AVM1, like the first virtual machine, is a historically grown thing that is programmed in something that Adobe calls ActionScript version 1 and 2. And according to a data set from Fukami, about like 80 to 90% of all the Flash in the world that you find on the internet is actually AVM1. That includes YouTube, YouPorn, and everything else you would care about. AVM2 is an ECMAScript engine. Like, it's very close to JavaScript, but it wouldn't be Adobe if they hadn't changed the specifications on several parts to make it more strange or whatever. It's programmed in something that's called ActionScript 3, not very surprisingly, closely resembling JavaScript, but then closely resembling. And the interesting thing is that theoretically that was a smart move. Practically, the whole clicky bunty, pixel pusher, RGB, Casper community has a real issue understanding OOP. And if you ever opened the native Adobe development environment for Flash, you understand why. Like, this is all built for ActionScript 1 and 2. If you actually want to write OOP code in there, oh my god. So here's the history, and bear with me, it actually has a reason that I tell you this. So the first scripting capability came in with Swift version 3, ages and ages ago. We were all running MS-DOS at that time. It was something like a very simple event handler. You know, they already had the concept of a button, so if someone clicked the button, it kind of like made sense that shit happens. So it would allow you to say, well, jump to this frame or loop the movie or whatever. That was very limited, so in version 4, they decided, oh, we need a full virtual machine. So they already put in a Turing-complete stack machine that has everything you need, like branches, conditional, unconditional subroutines. All the variables on that stack machine were actually strings. So if you had to add 2 numbers, you would actually push 2 strings onto the stack and then say add, and then the machine will try every possible way to convert a string into an integer, so they could add it and then put the string back on the stack. In version 5, they realized that was a very dumb idea. So they actually added typed variables, and since they're added, they also added a constant pool. So it actually, version 5 looks like someone briefly glimpsed into the Java specifications. And they're like, constant pool, types, cool, implement. They also introduced objects and methods, but that was probably the chapter they didn't read to completion, because like in version 6, they fixed all the OOP stuff in version 5, because they now actually allow early initialization, which makes sense for constructors in objects. They also have now the possibility to see if an object is actually an instance of a certain class. And then in version 7, they actually say, well, we need new function definition, and we could actually have object inheritance. And we could actually test whether an object implements a certain other interface. They also discovered exceptions. And mind you, like they bring in version 5, they bring typed variables. In version 7, they actually bring in a opcode that allows typecasting. Version 8 never happened. Version 9 apparently is where they actually had the AVM2 figured out, or found a specification of ECMAScript or whatever. And then version 10 is what we all have to deal with today. However, the reason I'm telling you this is it's all backward compatible. Everything is backward compatible. We still deal with the whole show today. So where would you actually expect AVM1 code in a Swift file? Like, where would you look for it? There's a tag, like the main data containers I mentioned, that is called do action. Now, they call their stuff action code, so yeah, that's where code is. There's also the do init action that I mentioned before, that is for early initialization. But then it bites you into the R's that we're actually talking about an animated graphics format getting code, because the define button to data structure that defines a button actually contains something called the button record 2. And no, it doesn't define 2 buttons. It actually means version 2 of that tag type. So it has a button record 2, and that can actually carry conditions, what happens when you press the button, release the button, blah, 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 which actually carry the code that's going to be executed once that happens. The same holds true for a tag called placeObject2 or placeObject3, which again don't play 3 objects but are the 3rd attempt in getting the data structure right. They contain something like clip actions. And a clip action is really interesting because it carries code, actually multiple pieces of code, that are executed when the shape that you defined is currently being obscured by another shape. Makes it very, very predictable how the code is going to be executed. Many tools that we have looked at actually turn out to only handle do init action and do action, even security tools. So you can easily have a shitload of code in a flash file and those tools wouldn't notice. So what is this code? The AVM1 bytecode is a variable length instruction set. If you speak Intel, that's what you usually face. It is either a 1-byte instruction that doesn't do anything except for the instruction, or it's an n-byte instruction that comes with a length field. So, mind you, if if, bold assumption, a virtual machine will actually validate the code it loads before executing. Given this information, it would always know what bytecode follows which other bytecode. So you would have an addressing that will actually go onto the instruction. But no, branches in the AVM1 are actually byte offsets. And they're assigned 16-bit integers to jump into a certain piece of other code. People with experience in code obfuscation and reverse engineering already know where that leads to. Now, the weirdest thing I ever seen in any virtual machine is this. The AVM1 actually has function declarations as a bytecode. So to declare a function, you're not actually like putting it into the file format or something. You have an actual virtual CPU instruction that says the next 600 bytes are going to be a function. That is smart. They can be nested. You know, my idea with this whole function thing is, back in the days at Macromedia, they probably had like free fridges with psychedelic drugs. And then, you know, that one guy realized, oh, the virtual machine actually needs functions, but like the guy that does the Swift file format took those mushrooms yesterday, and he's still tripping on them, so I can't talk to him. And he checked out the code, so I just put it into the virtual machine or something. And actually, like, the good thing is if you standardize the mistake once, you can call it a standard. So when they introduced exceptions and try-catch finally blocks, they actually used the same method. So there's some obvious weaknesses coming out of this. Like, the byte branch offset obviously means that you can easily jump in the middle of someone else's instruction. You can also actually jump out of the code block, so you can easily, and that is commonly used in exploits, jump it to an image or an MP3 that was part of your Flash movie. It also prevents large basic blocks. Now, I was really puzzled, and I'm like, okay, so how do they actually make jumps over more than 32K? Because they don't have a representation for that. But, well, I had Adobe CS2 Flash, which is version 10 of their Flash compiler. So, you know, take their compiler, make an if statement, make a big body in the if statement, and tell it to compile. It didn't complain, it didn't warn, it didn't do anything. It produced code that was invalid. So it will actually validate the condition and then jump as far as it could and execute half of the if body as well. The length fields on those instructions also have this brilliant property. They allow you to hide data. Because if your instruction actually has a 16-bit argument, it is really easy in the length field to say my instruction is 22 bytes long, which leaves you with 20 bytes for crap. And sometimes you also have an argument array, so you not only have a length field, but then you have a field that says how many arguments come, which can possibly say 0 and then stuff a whole bunch of stuff back to that. Also, as I mentioned, with the clipping, with the code execution on clipping, the order of code execution is actually very non-deterministic. It really depends on, like, is he seeing the shape currently, or is he not? And I kid you not, the Ganache guys, like a GNU implementation for Flash, they actually figured out that the code execution depends on how deep on the z-axis the object is that you're actually attaching the code on. So if it's further away from the viewer, the code is actually executed later. Makes all sense in the world. Now, well, they obviously did realize that, because they obviously put out a new entire virtual machine, the AVM2. So the AVM2 specification is actually, yeah, quite decent. It hasn't been updated since 2007, but apparently the open source release of parts of it, which is called Tamarind, is actually Adobe code, and apparently that's exactly what you get in the closed source as well. Now, in the specification, the first thing that I noticed was all the length fields are 30 bits. Everyone who does exploitation probably sees the rationale behind it. So there was one smart spec developer, like the guy who wrote the spec. And he's like, how can I prevent my suboptimal coders from fucking it up and having integer overflows all over the code? I just specify that my length field is a maximum of 30 bits. That means they actually have to add 4 values to get their integer overflow. That is smart. This is how you write good specs. But then again, they also use variable length integers. Let me tell you something about Flash and the whole stuff. So they love to build very complicated data structures to save about 2 bits. And then the next entry in the data structure says 2 bytes reserved, must be 0. This being a tradition, they carried it on in the AVM too. Now, so there's only so many ways you can have a variable length integer. And they're between 4 or 8, depends on how you call. So Adobe, with their sureness, picked the worst possible way to do it. So I actually had to check out the Tamarind source code to figure out how it works, because the specification wasn't clear on this. And this is what I found. Now, if you speak a little bit of C, let's ignore the style of this code and ignore the fact that you could actually do that in a loop. However, just watch the last 3 lines. So you're taking the last byte and shifting it 28 to the left and adding it to the result and then returning the result. How many bits did you actually parse? Is it 30? No, certainly not. So the lowest level reading function that is supposed to read your save 30-bit length fields of the Swift file, or no, of the ABC part of it, already ignores that specification and returns 32-bit. Congratulations. I hope the spec guy never saw that. He's probably dying or resigning. So what are the considerations for the defense approach here were, there are 2 types of attacks that we need to handle. One is malformed files that fuck up your Flash player. The other one, right? Who's calling me? Whoever it was, he hung up. So anyway, the second part being Flash files that are well-formed, but they use the API to do some stuff that you don't actually want to see. The idea was like, well, you could go ahead and try to fix the player. Kind of. You don't want to instrument it. The player is closed source. It changes all the time. So you will have to have a horde of reverse engineer monkeys or students or whatever your resources to constantly check where all the offsets went and where all the functions are. The player is extremely forgiving in parsing bullshit and executing it. So it's certainly not what we want. The player also only parses things that it actually needs right now. So for the website operator scenario, it's useless. And the player is written in unmanaged language, so every time they fuck something up, it goes boom. And seriously, nobody wants to write a new Flash player. So the idea was, let's try something else. Let's try something that I call normalization through recreation. Fancy name, extremely trivial way. So if the final consumer, which is the Flash player, is inherently fragile, as in it chokes on every wrong input that you can possibly give it, you need to actually filter it before. So what we do is we try to safely parse an SWF file, being really, really strict on the specification compliance and on the formats, then delete the original file and be left with what we understood of this file. And we create a new one. While we're at it, we can also just go ahead and patch the code that we're looking at and make it do other things. And then we take the normalized Swift file and pass it on to the original player in the hope that we clean it up sufficiently so it doesn't die. Introduction. So that tool was named Blitzableiter. Yes, it is a German term. Get used to it. The name was chosen because it takes dangerous electricity and turns it into a little blinky flash that doesn't do anything. So how do we safely parse? We take a runtime that will allow us to safely parse everything. It's as simple as that. So there is this discussion whether you should actually use managed languages or not. The performance issue doesn't exist, it's a myth. Then there is the only other issue that people say, like, real men code in C. Well, real men also fight battles with swords. Why don't I see the United States flying out people with swords? You mean, real men might do this, but like, it's the pussies who bring in the nukes. And like, in a defense scenario, I want to be the guy on the nuke. Also, it's the same lesson that we learned the hard way in crypto. Like, every time someone walks up to you and says, I have this brilliant new crypto protocol and I invented it all myself, you go laughing at him. But if he actually says, like, I followed everything Schneier ever published and I used all those proven algorithms, it can possibly be a good crypto protocol. So that's the same reason to build on a runtime that actually allows us good parsing, which is the CLR. It allows us to prevent any buffer overflow issues that we potentially would have. And in contrast to Java, we also get protection for integer overflows, which is really important in this scenario. We just ensure that we're not running any unsafe code, which the runtime allows. And since we're targeting .NET 2, it actually runs nicely on Mono as well. And the Mono guys don't implement the whole stuff so you can ignore it, right? They actually have a point of bringing this into open source operating systems. There is also a neat strategic benefit of running stuff on .NET. If someone finds 0 day against the CLR, your little fucking Flash parser is not the one he's wasting it on. He's going to take the biggest SharePoint site that he can find. He's not going to care about your Flash player. So, enforcing the container boundaries, which Adobe never does, is really easy in this scenario because we just allocate new memory every time we find a container, and then if things go out of the container, it throws an exception. We also really have to make sure that we also cover the case where the container actually didn't contain enough data to be full. So there would be stuff left, because that would be where I would put the shell code. So we have to make sure that the whole container was used. We only parse documented data. If you try to parse shit you don't actually understand, it's bound to fail. And the downside of this approach, of course, means you have to parse everything completely. Like, you can't get away with just parsing the things you're interested in. You have to parse the whole thing. And then check the input data very thoroughly on specification compliance. So is the format correct? Is it compliant with the version we're looking at? Are all the reserved bits set? Do the conditions make sense? Stuff like that. And then, of course, you want to do the code verification that nobody else does. So do the instructions actually have a legal length? Is it a legal instruction in this version? Does it actually make sense? How about jumping? Like, does it actually jump to another instruction beginning, or it jumps it in the middle of an instruction, which it is not supposed to do? Same holds true for try-catch blocks and for functions and all that. This is relatively trivial stuff. Like, you can take a linear disassembly and then see whether the jump points actually, the jump targets actually terminate on an instruction or not. And due to this brilliant idea of inline specification of functions, you can, of course, go ahead and specify 2 functions with bytecodes that would be overlapping. Therefore, we have to introduce a check that actually makes sure that every instruction is only part of one function, because otherwise shit goes wrong. Now, that leaves us with something that we consider a relatively clean format in terms of code and file format. However, it doesn't do anything about the people just redirecting your browser to the next exe download. Static analysis, provably thanks to this brilliant gay mathematician back in World War II, doesn't allow us to figure out what code does. If you find that out, I would be interested to know. It's called the halting problem, if you want to look it up. The alternative that we could have is we could emulate the entire thing. Like, we could emulate the AVM, see what the code would be doing, and then patch things that we're feeling bad about. The problem is we will automatically run into discrepancies where the emulation actually takes different conclusions than the virtual machine. Because mind you, we're dealing with a closed source, underspecified virtual machine that is very well known for fucking up stuff. So emulating that correctly would be a dumb approach in terms of prevention. What we can actually do is what we would do in dynamic analysis. In dynamic or runtime analysis, what we would do is we set a breakpoint somewhere in a code saying, this is where it actually happens. Here, all the arguments have to be assembled already. Like whatever obfuscation you did before, at this point in time, the argument, like the URL for redirect, must be correct. It can't be obfuscated anymore. We set a breakpoint here, and then we see where the URL is, and then we know what it does. However, when the code runs, we're no longer part of the show. We already handled the Swift file. So what we do is we actually patch those functionalities into the Flash file once we handle it. How does that look like? So there's an instruction called action get URL2. Yes, it's version 2 of an instruction that used to get to a URL. And that's the most common way for the browser redirects to work. When we get the Flash file, let's say we're running in the context of a web browser or proxy server, we actually know the origin. We know where it came from, right? So we can actually implement the same origin checks in the way they should have been implemented on the original runtime. And this is how that looks like. If you take like a regular piece of code, this piece of code in the middle here, the block is called ID31. Actually does have a get URL2. You see before, remember it's a stack machine, so you actually have to put all the arguments on the stack before you call an instruction, right? So this one here puts the arguments on a stack. It's a trivial case, it takes it from the constant pool. We're going to talk about this later. But there is a specific place where the instruction is actually going to be executed, right? So at this point in time, we know where it's going to go. So we actually patch the code to compare it with the origin that we came from. Essentially, what you see in the orange, it used to be orange on my screen, in the orange blocks, they got changed. So you see that the action get URL is actually one of two possible conditions. And you see, like, it's denoted 31.6. There's an action push that actually pushes the original origin that we're actually dealing with right now on the stack. It's Google in this case. It's the friendly version of Google, you know. They don't store data. They don't Vorratsdatenspeicher, Sie wissen schon. Anyway, so in case it doesn't match, in case the strings don't actually match up, it will just pop the arguments, the original arguments for action get URL2 off the stack and behave as if nothing happened. Otherwise, if they match, then we can actually go to the URL. Isn't that trivial? So, what do we need to patch? Well, Adobe published a list. Actually, PLS published that list in his secure development guide, and he's actually here. So, publish a list of functions that are potentially evil, where you could potentially have issues with. Functions that, or objects that accept URLs as strings, obviously push you to other websites or pull stuff from other websites. Functions that display or accept HTML. So there's text boxes in Flash, which Flash developers commonly take text from anywhere and put it into the text box, which is a relatively bad idea because the text box actually renders HTML, which includes JavaScript, which then, you know, makes it all interesting. We have a couple of functions that communicate with the web browser. We have flash vars, which, yeah. We have shared objects, local shared objects, which is also known as flash cookies. So you have a local storage that's independent of the browser, and no matter what browser you take, the porn site will recognize you again. And we actually have flat networking calls. This is all stuff we potentially want to patch. We also want to patch stuff that is not documented, like AS native. AS native is this brilliant function that you can call. You pass two numbers to it, which is a lookup in a table, and it will actually return a function reference to the native function that is behind this. So in this way, you can totally hide what you're doing. I also found cases where it does very interesting things. So how do we do actually patch? So our beloved Blitzableiter tool actually features an AVM1 assembler. So you go ahead and you say, if you see the following instruction in the following context, I would like you to patch it with this. And I would like you to make sure that you stay within the same basic block, that you fix up all the offsets, that the code is going to be valid afterwards. Which we actually ensure by running every Swift that we modified. We run it twice through the engine, which is optional. But like the second run actually verifies that the first run didn't fuck up anything. So we do support all the 100 documented AVM1 instructions. And we also have support for variable names. So you can actually write code and say, like, do this and that with $origin instead of, writing an individual patch for every website you visit. And it also supports randomization of variable names, which is like the cheesy virtual machine way of ASR. Because like the moment you put out a tool that has a variable that says check if evil, and that variable is called the same thing, the malware would just check whether that variable exists and set it to false, obviously. So we actually have to randomize the names. And then it gets interesting. Like most of the things we actually want to patch are calls to methods. So here we have an example. When a call to an object method is made, you here see a action constant pool, which defines the constant pool. And yes, every single instruction starts with the word action. I felt like a director writing this. So that actually, it pushes the variable name and the method argument individually on the stack. And then it says get variable, which retrieves a object instance pointer, which is then put onto the stack. And then it actually pushes the string of the method and says action call method, and then hilarity ensures. To actually figure out what there is, you first have to swap the stack, because first you want to get the object reference, take the object reference, get an instance of such object, compare whether those instances are there. Works since Swift 6 or 7. And then like exit a patch if that's not the type of object. If it still is, then check the method and then like clean shit up. Clean shit up is interesting. Like how do you make stack cleaning in a stack virtual machine? I'm not going to go into the full detail here because that's going to bore everyone. Already see people yawn. But essentially, it's really interesting to do a stack cleanup within the virtual machine, within a stack machine. This is how you do it. So you essentially pull all the arguments individually off the stack and then pull the function itself and then return undefined so the calling code actually thinks it actually called something. Oh, and here's the good thing about like the patching approaches. The patches don't have to be perfect. They should be logically sound. But they don't have to be perfect. Because the AVM is so forgiving in what it does, you can easily fade half of the variables to setting like, the type undefined. Shit wouldn't crash. If the AVM will actually be implemented like every sane virtual machine, they wouldn't have a customer base anymore. So the virtual machine just ignores every glaring programming error it finds as long as it can safely continue to make blinky objects. So what we see here is an example of the famous Gnida malware. To the left, the blue thing, that's the regular basic block graph of that malware. It actually only has one code location. What you see to the right is the same malware, and the little red dots that you see in there is all the shit we patched. And then on top of this, you see the structure that was introduced above the white bar. That's actually a function that we introduced that does all the object checks, so we don't have to patch them in each individual place to keep the code inflation down. Now, what does it actually do? So we've added a couple of malware samples. You see it's only 20. Because it's really hard to get to actual Flash malware samples because they're usually hosted by advertisement hosters. And at some point in time, it becomes really boring to click reload on porn sites. we had like 20 unique things that did unique things, and not just all redirected your browser somewhere. So if it's AVM2, right now we can either let it go through or drop, because we don't support that yet. All exploits that were actually targeting the runtime itself, like Mark Dowd's exploits and all other incarnations, they all fall for the format violations because they get validated. You need, if you ever wrote exploits that are based on like fucked up file formats, if that file format is correct, then you're not exploiting anything. That is the downside, and this is what we're actually playing on here. Everything that uses obfuscation in the malware code is obviously eaten right away, because, well, you can do a lot of bullshit in the instruction set. People obviously do it, but it's a clear indication that you don't want to see that type of porn. All exploits targeting the browser itself by redirecting it were patched to harmlessness. So far, we're pretty happy with the results. Of course, we have collateral damage. People tend to think that their flash files contain highly valuable intellectual property that they cannot possibly give to the entire world. Secret, if you're uploading code on a web server that is supposed to be anonymously retrieved and executed on the client side, it's no secret, no matter what you do. However, there are people that actually buy obfuscation software, and this obfuscation software obviously creates invalid code. So we drop it, except for one that's called Airfuscator that actually produces valid Swift files. And then, of course, the question is, does the porn still work? So Fukami actually I mean, if the porn didn't work, we could have used NoScript, right? So Fukami was nice enough to provide a very large test set. Not of porn, of flash files. So it's like 95,000 files, 45 gigs. We pushed it through the engine. 92% of the files actually validate in parsing and validation. So they're actually considered fine from a format point of view. And a sizable number, 82% actually survived the whole patching process as well and then still work. We do have an average code inflation of 224%, which is a lot and needs to get fixed. But first, performance. Because people always say, you know, it's .NET, it can't be fast, and like, why didn't you write it in C? So it's half a second to validate it and half a second to patch and rewrite it. I can wait that 1 second. But I have to admit that my machine is quite decent. If I do that on my laptop here, it would be different. So there's an obvious and a less obvious problem. The obvious problem is we're patching all the code that inflates the code massively. So the flash runs slower. I couldn't care less. However, due to this brilliant idea of having a 15-bit branch destination limit, we can actually run into the situation where we patch stuff in, and then we have a branch that would need to go over our patch, and it actually integer overflows, which we happily catch because we're running in the CLR, and we're not having to test that individually. But some flash files, especially stuff that's not coming out of Adobe's compilers, but from actual, real backends, they actually max this out quite a lot. Like the YouTube player, for example, has a number of instances where the jump would actually be not possible if it would have been 1 byte more code in the middle. So we actually need code flow analysis. Not a big surprise, you already have seen the code flow graphs. What we will introduce is jump paths in the code. So if you have a long jump, you actually split it in 2 small ones. The whole thing with this is, if they didn't have inline function declaration, I wouldn't feel bad about it. It would be a trivial algorithm. However, they do have this inline function stuff that can actually be nested as well. So we don't actually know how smart of an idea that is to put right in the middle of a function, which is not actually going to be executed, but we're jumping in and jumping right back out. And I don't actually want to kill the AVM with that. I'm also blessed with people to work with that can, right off their asses during lunch, come up with pathetically complicated code examples where a naive approach wouldn't work. And those people pointed out this is not actually trivial. What we will also introduce to counter this code inflation is something that I call stack tracing. So we already have an object, a class representation for every single instruction. So we can actually go ahead and put the stack behavior of that instruction into that class as well. Figure out from the point of potential patching, go the way back and figure out like, what is the stack containing? Is it constants? Is it going always to the same website? Well, then we can save the patch, right? This would already be done if I weren't such a fucky coder. And you know how the train of thought is different to the real train? And because the train of thought can actually make a 90 degrees right and then go all the way into the pampa. That's what happened here. So I actually wrote a lot of code that was then later deleted. Things Blitzableiter can't do anything about yet. One is heap spraying. Obviously, you can use Flash to heap spray. If you have a browser exploit, you just put a Flash movie in that creates a shitload of interestingly colored shapes, and this color will actually be your shellcode. That is relatively trivial to do. It's pretty hard to actually tell allocations apart from legal to illegal allocations. Microsoft Research has some relatively new good work on this that we're going to check out and see if it actually makes sense in a Flash context. The Flash API overflows aren't really there yet, but we're seeing them by the metric ton in PDF now, which happens to come from the same company. And so like every third JavaScript function in PDF that accepts a string apparently doesn't like long strings. And once PDF is done, I'm expecting a lot more people to look at the same topic in Flash. So we would need to actually check individual call arguments. That would be similar to signatures in AV, and you probably have an idea how much I like that idea. So what's the current state? Now, it isn't completely done yet, as all software ever is. We only cover the tag types that actually carry code. First of all, there were the interesting ones. Second of all, well, now there comes the task of actually writing all the code to parse glyph sets, image formats, MP3s, and stuff like that. Because otherwise the approach isn't actually worth it. We actually have to parse everything. Like the latest exploits against Flash were all with malformed JPEG content, as if JPEG was such a new thing to parse. We will need to support AVM too. I already started it. Got a bucket, puked in, and decided that we first handle AVM1 completely. But a little of the code is already there. So why do we actually go open source with this? I'd like to think of Kerckhoffs's principle from crypto to be actually applicable to most of the defense strategies that you run. Security by obscurity actually does work. I mean, ASLR is pretty much nothing else. Like, it's just very obscure where you have to return to. Other than that, it's nothing special. However, defense mechanisms that are auditable, where people can actually look into it, see how does that work, is that principle sound, are, in my world of view, preferable to big yellow boxes that somehow make you secure and someone else rich. Because usually they only fulfill the second requirement. And it's not like I'm the best coder in the world. And it's not like you want to trust my code to protect you, even from porn. Also, I want the Flash developers to be able to test their stuff. And like, if their code is like 500 times bigger than it was before, maybe you shouldn't use those dynamic data structures to find a single URL that you hard-coded somewhere else anyway. And we want to, like, this, it gets released as a library, so people can actually integrate it into Firefox, into Squid running on Mono or whatever, or even make it a WordPress plugin. We don't really care. So, that's the yellow label is actually the new NIST certification for security be so, seriously, that's the website. Every non-native, not German native speaker, find a German of your liking to like spell Blitzableiter for you until your browser wrecked. Ah, geil! Awesome. Well, yeah, I'm famous for fuck-ups like that. So the DNS record is actually spelled correctly. So I think. Yeah, the problem is if you do English slides, you have a red line under this word all the time anyways. You don't notice when you spell it wrong. No, it doesn't. I like the fucking name. So, but I will do a redirect. How about that? This is what you got DNS for, right? You can be as bad as you want in spelling. You can have a C name and fix it all. So the site contains the source code. We actually do have developer documentation to get you started. So it's not like read the source and find out. We do have test cases, and you can fire bugs against me. So coming to an end, I'm doing on time actually. So here's an FAQ. So what about the other technologies, Adobe Air, Flex, Fleur, Fart? This one is about Flash. This is open source. Go try it yourself. Does that approach, if it turns out to be useful, can it be used on other Riot technologies? Yes, I think it could in principle. You had to re-implement it, but yeah, maybe. And yes, we did look into other runtimes. And in my humble opinion, if you want to actually see how it's done right, read the articles about the security architecture and exploit prevention in Microsoft Silverlight. There's actually people that know how to do this correctly. I call you back, FDR. So here's my acknowledgements. First of all, to Thomas Kaspers and Daniel Löwenich from the BSI, because they're among those guys that I mentioned in the beginning of those talks. This talk, and they're really, really good and smart people. I would also really like to thank Fukami, because without him I would still be wondering what this whole Flash thing is about. So he really, really helped us to get into the subject and understand how the world looks if you're not a coder but you code. And to my people, Dirk, Mumpy, Gregor, and Jörn, for general awesomeness and being good sounding boards, and for Aaron and Kurt for providing samples, because they're really hard to come by, like actual good Swift exploits. And I think that was it, and I hope to see you guys at the Fanlight party tonight. So, the talk might suck, but the party is going to be great. Thank you. Huh? Do we have time for questions? So, we do have time for questions, actually. And I do have a special guest for the questions as well. Where's my special guest? It's not coming? Pilas, are you in the room? Okay, no special guests. Go ahead.
All right. I'd like to know how you know so much about the Flash file format. I mean, did you read any specs? Did you get them for free, or did you have to sign NDAs or stuff
No,
like that?
the specs are actually public.
Oh, really? All right.
And they've always been public. They're just not very precise.
All right.
Like take the specs and a hex editor. You will spend most of the time in a hex editor, but it does make sense at some point in time.
All right. And how did you obtain these nice code flow graphs?
Huh?
The code flow graphs, how did you obtain them?
How to obtain them? Oh, there is actually code in Blitzableiter to get them. Like it generates the basic block graph out of the code.
All right, all right. And then the final question, is a Flash code able to modify itself?
No, it's not. AVM2 is able to create new byte arrays that will then be loaded as code, which is then again a point where you can patch. But there is no self-modification per se.
All right. Thank you.
Sure. So we do have a special guest. Do you introduce yourself, please?
I'm Pellis Yuli from Adobe. I actually work on Flash.
So that's your applause. So in case you actually have a Flash question, I will defer to him. Good.
Hi. Hello. I was wondering about the approach to avoid, to compare the URL to check if it's coming from the same place. On one hand, wouldn't this avoid having links to other websites?
Oh yeah, that's the entire point.
Okay. And then what about, because you can load content from XML, the URL can be defined outside, or you can load the malformed JPEGs from file system.
Yeah, we only actually control what the Flash code does. If you, for example, load an XML and then the Flash runtime decides to get the DTD from some third-party place, we can't do shit about it.
Okay.
Yeah. Hello. So my question is probably directed to the Adobe guy. The question is, FX did an awesome job, but of course I can't expect to fix your bugs, or to fix him your bugs, and that's on a global level. Flash is probably very likely installed at 99% of all important computers. So will Adobe take any actions to my fixes specification, to my reduce the risk which do arise from using Flash? And this on a level where probably all implementations, also Ganesh and so on, is considered. Hard question.
Okay, I heard bits and pieces of that question because of the noise. Is the general question, what is Adobe doing to better protect the Flash platform?
Exactly, because I can't expect FX coding always some protectors for your software.
We are continually taking measures to secure the Flash platform. We have a team of security developers that implement a secure product lifecycle and all the things you would expect to go along with that. We have fuzzers running on it 24/7. We have stack analysis tools being run over it. All the good things that you would expect. But we also support the work that he's doing with Blitzableiter because as Microsoft has shown, Microsoft has the most mature SDL out there, and they still have issues from time to time with their code, with IE, etc. So groups will always need to have a defense in depth architecture. So we think the work that he is doing in general is good in principle to help further the defense in depth approach for certain organizations because they for instance, even when we put out a patch, some enterprises can't immediately adopt the patch because they have to go through a certification phase, et cetera, which has a window of opportunity for an attacker to get in there while they're certifying that it will work with all their software. So, so we are also supportive of work that, like what he is doing in terms of being able to help protect enterprises with the second layer of defense or defense in depth in addition to what we are doing.
Yeah, well, and my second question would be, are there any plans to may drop the backward compatibility someday? Because it really sucks. I mean, he pointed it out too. And backward compatibility was also a heavy issue on Microsoft OSs, at least from my point of view. So maybe in version 12 or 20, you might, because I don't think you can fix everything because of the backward compatibility without breaking stuff. So the only way to do it right would be probably to may drop it. What's your opinion?
So the question is, what's our stance on backward compatibility? Are we always going to try and maintain some level of backward compatibility? Is the basic question. For now, we are supporting the older bytecodes because, as he pointed out in his presentation, a large majority of the content is still created for the older AVM. So switching at this point to strictly enforcing AVM2 would break the majority of the content on the web. We do make backwards breaking changes from time to time. We did so, for instance, when Rich Kennings did his research on vulnerable Swift files on the web, we made backwards breaking changes. We made backwards breaking changes for DNS rebinding to address socket compatibility issues. So there are times when we will make the call that it's worth breaking the internet to fix an issue. So we just balance, or always in a constant state of trying to balance both of those. So we're not completely against backwards breakage. We've definitely done it in the past, but we also have to try to keep the web working.
Thanks very much.
Thank you.
All right, give these guys a huge round of applause again.
That was great because